Hello guys, and welcome to another calculus video. In this video we're going to be taking on this quite interesting integral right here. It's the integral from 0 to infinity of the error function of x squared over x squared dx. Um, as a reminder, the error function of x is essentially the integral of the it's essentially the fractional a portion of the Gaussian integral. It's the integral from 0 to x of e to the negative t squared dt, all multiplied by 2 over square root pi. So as you can see, limit as x goes to infinity of error function of x is equal to, not 0, sorry, 1. And so we're going to be evaluating this integral right here. It's going to be a little bit of a shorter video, but I think it's pretty interesting, so let's go ahead and jump right into it. So the first thing we're going to want to do is sort of simplify this a little bit because if we go ahead and directly substitute in the definition of the error function here, we're going to get 4 over pi, because we have 2 over square root pi squared, right, times the integral from 0 to infinity of the integral from 0 to x of e to the negative t squared dt, all squared, over x squared dx. And it's kind of nasty to deal with this because if we were to expand this into two different integrals and then reorganize everything, we'd end up with like a triple integral, which is not fun to deal with. So what we're going to do instead is we're going to do integration by parts to make this a little bit similar, a little bit easier to deal with. So we're going to integrate 1 over x squared, and we're going to differentiate this nasty integral squared. So we're going to get 4 over pi times the integral from 0 to x of e to the negative t squared dt squared over negative 1 over x, right? Evaluated at infinity and at 0. So at infinity, obviously, this is going to be constant because we know that the Gaussian integral converges, and this is going to be infinity. So that's just going to cancel out. And at 0, I want you to note that e to the negative t squared is equal to 1 plus everything on the order of t squared and above. I'm not very good at using big O notation, so this might not be exactly correct, but everything else we have is in order of t squared and above. So if we integrate this, integrate from 0 to x of e to the negative t squared dt, we're going to get x plus stuff that's on the order of t cubed, right? And the reason this is important to us is this tells us that when we square this, right, we're going to have x squared plus order, I don't know, something bigger than that. I guess the lowest order would be x to the fourth. And so when we take the limit as x goes to 0, we're essentially taking the limit as x goes to 0 of x squared plus o x to the fourth over x, which is just going to go to 0 because both of these are going to be 0 on the top. And so that's really important for that limit right there because we have that 0 in the bottom. So let's go ahead and calculate what the rest of our integral is going to look like. So we're going to be adding the integral from 0 to infinity of 2 times our other integral. I guess we're going to have just 8 over pi here, and we can get rid of that 2. Comes the integral from 0 to x of e to the negative t squared dt. Then by the chain rule, we also have e to the negative x squared, and then we're just dividing by x dx. So let's go ahead and reorganize this. We're going to get 8 over pi times the integral from 0 to infinity, and we're going to rewrite this as a double integral, so the integral from 0 to x of e to the negative x squared plus t squared all over x, and then dt dx. Now I'm going to go ahead and just rename t to y to make this a little bit easier to conceptualize. So t is going to be y, and so now we have a little bit of a fancy double integral here. Now, in order to easier evaluate this integral, clearly, when we see this x squared plus y squared, this makes us think of circles, right? And so I'm going to show how we're going to use a circle in order to evaluate this integral. So if we visualize the area that we're talking about here in the xy plane, everything's in the first quadrant, so we can just draw it like this. This is going to be our y, and this is going to be our x. And obviously of importance is the line y equals x. So we can see that x is going to go up to infinity, so we don't need to worry about that. And y is going to go between 0 and x. So we're going to cover all of this area right here within this little sector. And of course, this line right here, we already stated, is the line y equals x. But for those of you familiar with polar coordinates, you know that this is also the line theta equals pi over 4. And since this goes all the way out to infinity, we could say that it's the same as being a circle out at infinity. And so this means that we can make a very important substitution in multivariable calculus, which is our polar substitution. So x is going to be r cosine theta, and y is going to be r sine theta. Now, obviously, r is going to go all the way out to infinity, and our theta is going to go from theta equals 0, which is right here, right? Theta equals 0, all the way up to theta equals pi over 4. So let's go ahead and rewrite our integral. So when we have our e to the negative x squared plus y squared, when we set x equal to r cosine theta and y equal to r sine theta, this is just going to become negative r squared. And then when we're dividing by x, that's just going to be dividing by r cosine theta. And before we put our differential in, we have to remember to add the Jacobian right here. So the Jacobian is very important in multivariable calculus, and it shows us how to get a differential when we're talking about two variables. So we're going to go ahead and calculate the Jacobian real quick. So Jacobian is going to be the determinant of the matrix dx over dr, dy over dr, dx d theta, dy d theta. And once you go ahead and take all those partial derivatives, these should all be partial derivatives. I just wrote them incorrectly, I guess. Yeah, I guess I should do that. And then once you go ahead and take that, you're going to find that this is just going to be r. So we need to multiply by r before we write d theta dr. And that r is just going to cancel with this r on the bottom. And so we can separate these integrals, and we will get 8 over pi times the integral from 0 to infinity of e to the negative r squared dr times the integral from 0 to pi over 4 of secant theta d theta. So we're going to get square root pi over 2, of course, for our Gaussian integral. So we're going to get 4 over square root pi times this integral, which is just going to be natural log of secant theta plus tangent theta. That's the integral of secant, evaluated at pi over 4 and at 0. And so at pi over 4, we're going to have square root 2 plus 1, and at 0, we're just going to have 1, so that's going to disappear. So overall, our answer to this awesome question is going to be 4 over square root pi times natural log of 1 plus square root 2. Anyways, that was a pretty straightforward problem. I just really like the way that we're able to reorganize an integral defined function in another integral into a sort of a polar graph, which I thought was a really interesting way to transform the problem. So yeah, I hope you guys enjoyed the video. If you have any suggestions, feel free to leave them down in the comments for more integrals. And yeah, see you next time.